All right. Okay, everybody. Welcome to our fourth episode, I think, of Robo Papers. And today we're super happy to have Jason Ma with us today, talking about his paper, Visual Language Models Are In-Context Value Learners. So, Jason, welcome to the show.
Yeah, thank you for having me, Michael and Chris. Super excited to see you guys.
Well, likewise. So yeah, maybe just a quick one for the audience, who don't know about you. Could you share a little bit about yourself? How do you get into robotic research in the first place?
Yeah, of course. So hi everyone, Jason. I'm a final year PhD student at the University of Pennsylvania. And these days I'm spending time in the Bay Area. And how I got into robotics research. So when I was a kid, I played the game of Go a lot. So when AlphaGo came out from DeepMind, that's when I was in high school. That was a huge shock for me, right? Like I was like, wow, AI can actually solve this super complicated game. And that got me really into reinforcement learning. So I started my PhD, did reinforcement learning. But then after a while, I realized I want RL to have a real impact somehow. And I decided to do RL with robotics. So that's how I got into robotics. And if you look at some of my papers, they all have trying to solve or address some elements of reinforcement learning in the context of robotics. So that's how I got into the field, and spent some time at DeepMind working on this paper that we will talk about, and also spent some time at Meta. I think I overlapped with Chris when I was at Meta many years ago now, and also spent some time at NVIDIA. Yeah. So super excited to be here and just sharing some of my work and, talking to you guys as well. Yeah,
that's awesome.
We're excited.
Maybe as a start, as a start, perhaps you can, start sharing your screen, and then we can just dive straight. If you can just give an overview of the paper, and then we can go from there.
Yeah. All right. Can everyone see my screen? Okay.
Yep, perfect.
Yeah. So today we're going to talk about my paper done at Google DeepMind last year titled Visual Language Models Are In-Context Value Learners. So this paper will also appear at iClear 2025 next month. So what this paper is about is... So I think in robotics, or in general, in embodied intelligent agents, it's really important for the robots or the agents to be able to keep track of their progress, right? Because keeping track of progress on their tasks is the way for the agent to know whether or not they're doing a good job at the task or doing a bad job at their task. So this allows the agents to improve using their experience. We're using other data on which we can provide some labels on how much progress the particular episode or particular actions has made. And traditionally, doing that, learning that is very difficult. And actually, you have to do something called a value function reinforcement learning, which essentially tells you how good your particular state or particular state action pair is for solving a task. And that's really hard to learn. So in this paper, what we did is actually a very simple method. You can actually take today's best visual language model, that's taking images and a text and outputting other text, and forming the problem of predicting progress for a video or for a particular frame as a prompting problem for visual language model. So you can provide the VLM, the frames of your robots doing the task, and providing some language label for what the task is, and have the visual language model zero shot, without any training, just predicting progress within its context. And surprisingly, this method actually works quite well. So out of the box, it could predict progress for fairly complex tasks, such as here in this figure, folding dress, and also hundreds of other tasks and across many different robots that we tested using some of the open source robotics data sets in the open cross-embodiment data sets called OXE, and also some internal data sets available at the time at DeepMind. So I think this was a very good example of how to use large foundation models and visual language models to really make traditionally very difficult problems in robotics much easier to solve. So in this case, just being able to give robots a sense of progress in its task. And so why is that useful, right? Because you can use this to really help robots improve. And as we will show in the paper, also it's a good way to just filter out good data versus bad data without any manual annotation. Because traditionally, if you collect a lot of data for robots, some data are good, some data are bad, but it's really tedious for humans to manually pick them out. But using this algorithm, you can actually just run all your data through the VLM, and the VLM can sort of tell you which data is good and which are bad. And that's really useful, especially these days when the community is very excited about learning on large scale data sets. it's very useful to have a VLM that you can just plug into your pipeline to automatically curate high quality data. So I think that's a very high level summary of what this paper does. And I'm happy to jump into any detail. We have a website where we have a lot of
you were just showing us
interactive demos as well.
It says input shuffling on it. What was that about?
Yeah. So this is
so I understand
some of the technical
so
detail in the paper. Yeah. So what we found is for vision language models, if you're passing a video in the original temporal order, then the model is actually likely to hallucinate a sequence of predictions just monotonically increasing, right? Without actually paying attention to whether or not the video actually made progress towards the task, right? So for example, you have a video of the robot attempting to fold the dress, but it's not very successful at doing so. But if you present the video in the original sequence, in the original temporal sequence, because there's a lot of correlation between an earlier frame and the frame that comes right after it, right? Because they are just appearing right next to each other in time. So the delta between the frames are actually very small. And it turns out the vision language models today, or when we were testing this, such as Gemini 1.5 Pro or GPT-4o, it's very likely for the model to hallucinate because it just sees, here's a video that's progressing forward in time. So it must be making progress towards solving the task as well, right? So there's a lot of cases where when the video is actually not making progress but temporally coherent, the model would hallucinate good, or like monotonically increasing, task progress estimation. So by shuffling the frames, what we were able to do is to break up such temporal correlation. So the model has to pay really close attention to the individual frames in the video, and then try to predict the progress for each of the frame in the shuffled order one by one. So it's kind of like a way to force the vision language model to pay attention to each individual frame in the video. And actually by shuffling, there's a pretty interesting artifact or like a result, which is that if you shuffle a video, like a good video, right, you shuffle it, then there should be like a unique way for these frames to be shuffled back into the original order, right? And you can actually use the shuffleability of a video as a way to judge the quality of the video. So as an instance, as a negative example, if your video is, a robot just like waving its arm back and forth, right? So you see like a lot of the frames have the identical frames repeated many times in the video. So if you shuffle it, then you actually lose all the information to shuffle the original video back.
Really interesting.
Because the same frame appeared many times in the video, right? Many times in the video. So, there's like so many equivalent ordering to shuffle the video back. So there isn't a unique ordering. But because in most robotics manipulation tasks, unless the task requires some cyclic behavior, right? You're basically trying to manipulate the object to certain configurations, so you don't really repeat the same state twice. You can actually use the shuffleability of the video as a proxy for how good the original demonstration is as well. So we actually demonstrate how to use this to do data quality filtering, which I think is like a very neat and nice way to use this like value prediction capability of vision language model that, people haven't really thought about before. So I think that's what's really interesting about this shuffling method as well.
Yeah,
I think the downstream
applications sorry, Chris. No, I was going to say like the downstream applications from this, I think is just tremendous. But before we, I think, get to those applications, if you can just like get the audience a bit more concrete, like what exactly do you mean shuffle video? Like, are you loading these videos in context just to this Gemini or GPT-4o, this VLM? And then I saw in your appendix, you literally coded a few paragraphs in text. Yeah. Could you talk us through? Because I think people may not get how simple it is. Like when you say simple.
Yeah. So today's visual language models have really long context. So they take images for text as inputs, but typically they can take many, many images. Right? So if you think about a video is just like a sequence of frames, if you will. So what we did in this paper is that you quite literally take the video, but of course subsample a bit, right? Just because otherwise, based on different recording frequency, you might have really dense, like long videos or really short videos. So we just subsample different robot videos to the same like frequency or same number of frames. So in the paper, we did it to be a maximum of 30 frames. So we just feed it into the context of vision language model. And at the same time, like you mentioned, we have a prompt for the model. When here's the prompt. It's a fairly, it's like a paragraph, but, it basically says you are trying to predict, task completion or task progress for a task. So here's your language prompt for the task is, and it goes from 0 to 100. And you just basically provide all the frames that you're going to pass in, but you tell the model that these are in shuffled order. So you have to, pay attention to each individual frame and predict the progress for each one by one. So once the model gives you a prediction, you can basically parse the prediction and then figure out the actual task progress estimation for each of the frame you pass in. And I think one thing that's really important for this method is that whenever you have a video, even if you shuffle the video, right, you actually do know which of the frame was the initial frame. So we actually additionally tell the VLM, here's the initial frame of the task. So why do we do that? Why is it important? Because for many tasks in the real world, the forward sequence is as feasible as a backward sequence. What I mean by that is, let's say you're trying to open the door. If you play the video backward, it's a video of closing the door, right? So both are valid. So if you present a shuffled sequence of frame, then reconstructing the shuffled sequence of frame into both the forward order and backward order is both plausible, right? So you need to tell the model which of the frames the first frame to break up such symmetry. So that's important for a lot of the real world tasks, which is somewhat reversible. That's what we provide. And because you have the video to start with, you can just take the first frame of the video as the initial robot scene. But that's basically you have this prompt.
But you're providing frame 1 to n at the bottom. So why do you need to do that separately there? If you know it's frame 0.
Yeah, because these frames are in the shuffled order, right? So the frame 1 here is not actually the first frame, right? We call that.
I see. Yeah. So that's
right.
not.
Yeah.
That's not, okay. So
whatever appears here.
This is the one. Okay. Yeah, it makes sense.
Yeah. Here is all shuffled up, right? So that's why you need another one that's specified. Here's the anchor. Here's the actual first frame. And now I present you a bunch of shuffled up frames. Tell me how much progress each one's made for the task at hand. And we know it should be somewhere between 0 to 100. Yeah, cool. Okay.
Yeah, and you mentioned, in the paper, you use something called VOC to evaluate, I guess, the value evaluated. Yeah. Could you talk about what's VOC basically?
Yeah, so this is one of the contribution for the paper. So I want to take a step back and just talk about, if we have a model that can predict task progress, how should we evaluate it, right? So, this is a standing problem in reinforcement learning at large that I'm just trying to find where it is, right? So let's first talk about what VOC is, right? So VOC stands for value order correlation. So basically it computes the linear correlation between the predicted task progress from the VLN, by sorting them according to numerical increasing order with the ground truth, a temporal order, right? So if your video has 30 frames, this is just basically 1 to 30. And then once the model predicts the task progress for each of the shuffled frame, you can arc sort them to get them into the increasing order and compute the correlation between that and the ground truth order. So why do we do this? So traditionally, it's very, very difficult to evaluate a task progress estimator for a model that predicts task progress, because how do we know what's the ground truth task progress? And if you have a suboptimal video, you actually, if it messes up, let's say you only accomplishes half of the task, and towards getting there, there's a lot of random actions in the middle. It's really hard to know what should be the ground truth task progress that these intermediate actions make towards the goal. Traditionally, to show that such a progress estimator is actually good, what people do is typically actually run reinforcement learning, try to learn a model using the progress estimator, right? Because the progress estimator allows us to differentiate good and bad action. So using that, it should help the model learn, right? But this is a fairly expensive process because reinforcement learning is pretty expensive. You have to train a model from 0 to completion to actually be able to solve the task. And if you want a method that's supposedly universal, being able to provide task progress estimation for any task, if you want to evaluate it using the traditional method, then that requires you to do reinforcement learning on all the tasks you're testing. And that's very infeasible and hard to scale, especially at the scale that this paper does, which is hundreds of tasks, more than 20 robot embodiments. So clearly we need a more offline way of evaluating the goodness of a model that can predict task progress estimation. So that's why we came up with this metric in the first place. So why is this metric a good metric? Well, so a progress estimator, in the worst case, if it doesn't do anything else, we know that the progress estimator should be able to predict task progress on a optimal expert demonstration, right? But we know that in the expert demonstration, every frame in the video, the robot is getting closer towards the final goal, right? So the ground truth sequential order of the video is actually a pretty good proxy for, whether or not that a good proxy for the actual task progress is happening in the video, right? So if you have a robot video that's going from 30 frames, then the first frame is maybe 1 out of 30. The second frame is 2 out of 30, all the way till the end. So then if you have a model that's predicting task progress, then the model's prediction of the task progress should be very much correlated with the ground truth progress, right? So we can run this metric on tons of expert demonstration videos to at least know whether or not the model is doing good prediction on good demonstrations. But of course, this doesn't cover all the cases. What about bad videos, right? So if you think about bad video, like I mentioned, right, once you shuffle the video, when you shuffle back, it's really hard to shuffle back to the original order. So because of that, the ground truth order and the predicted order should have really, really low correlation, right? So then you can use how good the correlation is to determine whether or not the video is actually a good video versus a bad video. So that's how we are able to come up with this metric, and actually show this metric is pretty informative on telling, first of all, whether or not a model that predicts task progress is good. Well, we know the queried videos are good. And the second, fixing a method, we can use this metric to tell apart good videos versus bad videos. So that's some of the experiments we show in the paper.
Yeah. Yes. Sorry, Jason, could you zoom in a little bit to this chart? So what you're saying here is that so the VOC range from 1 to -1. 1 meaning is just perfect correlation, and then -1 is just totally opposite. So what you want is what you have here, which is very right-leaning, where presumably these are all your super expert demonstration that you just spoke about.
Right. So so let me talk about this figure a bit more detail. So OXC dataset is a large academic combination of different individual datasets. Right. OpenX embodiment. And typically in most of these datasets is robots demonstration. So these are expert demos, right? So as I said, a method should achieve pretty high correlation if it's a good progress estimator on the OXC dataset. So that's indeed what we show. Our method, which is called generative value learning, because it's using a generative VLM to do value task progress estimation. You see that it's doing fairly well in the OXC datasets, whereas the baseline, which is called LIT, which is actually also a paper that I wrote a couple of years ago, is actually quite random, meaning that it's not able to generalize.
Google is better. So that's...
Well, yeah, it's some work I did with collaboration with Meta a long time ago. You see, it doesn't have the generalization capability, right? So that's what this figure is really showing. Just to show GVL is actually a very good progress estimator, at least when your demonstrations are quite good.
Yeah. In fact, I think you have a follow-up figure. I think figure 7, if you can go there, that gives a similar picture. I think here you differentiate between success and failure. Could you talk about this a bit?
Yeah. So this is exactly what I was talking about for using value autocorrelation to differentiate good trajectories and bad trajectories, right? So here we have some failure trajectories collected in simulation. So if you look at some of these trajectories, the robots, just trying to grasp the object many times and don't succeed. So in those trajectories, if you shuffle the frames, you cannot shuffle back to the original order. Therefore, if you try to predict the progress for those videos, once they're shuffled, you are not going to have really good correlation with the ground truth order. And what we show here is that in over 1,000, I forgot the exact number, 1,000 success episodes and 1,000 failure episodes, the distribution of the VOC for the failure episodes is pretty uniformly random, right? As you would expect. As for success episodes, you see that, again, very much right-leaning. So once you have this, you can actually just, set a certain threshold for the VOC as a way to, filter successful trajectories or to classify a trajectory as success or failure, we show doing that is actually giving you much, much higher accuracy, precision, and recall over successful versus failure trajectory in comparison to just using the VLM and ask the VLM straight up whether or not this trajectory is successful or not, right? So this is showing one usage of doing task progress estimation on mixed quality data sets, and then you can use it to do success detection as well.
So, sorry, Jason. So I was trying to, when I was looking at this chart, I was wondering if there's a scenario where some kind of failures are very left leaning, right? Because right now your distribution of the failures is kind of, spread evenly across the, like the 1-to-1, right? For VOC. I wonder if there are, presumably it's because the way you set up a simulation is very random. But that's why they are random. I think that's the reason, right? Okay, got it. I see.
Yeah. I think it's possible to have very left leaning progress if failure is deliberate failure, right? Like you're deliberately trying to
deliberate
fail at the task instead of like the model is just actually not good enough, so most of the actions appear random.
Yeah, this is something I always, as a layman, I think about, like, because like the way I think about how I learned when I grew up is actually typical Asian parents is like, don't do this, don't do that, like negative example, don't do this, don't do that, and that's how we learn.
Yeah.
So yeah, but maybe the typical RL setup is not like that. It's mostly trying to learn from like within success and whatnot. Okay, cool.
Yeah. I think this is the method as presented this way is pretty applicable to like models' own failure data. Because if you look at how models typically fail, they fail and they just kind of like get stuck and not make so much progress. And those are the perfect examples of failure where once you shuffle, you just lose information on which frame actually came first, just because all the frames are kind of visually similar to each other. So that gives you a way to automatically use this to filter bad trajectories during like, robots is trying to learn on their own, for example.
Got it. Sorry, I have multiple questions. Feel free to jump in, but I do wonder, like, so presumably, I think you have another chart that kind of show as the temporal sequence goes through, like the value estimator do actually climbs up, right? Kind of responding to the temporal effect. But I wonder if there are some, maybe say, these charts, right? So in general, it should go up and right. I wonder if there are some longer horizon tasks in the physical world where literally it's kind of like a puzzle where maybe the few steps before the last final outcome is something that looks very suboptimal. It's like, in the typical old school kung fu movies where the master would do something that looks very dumb, but actually it looks very dangerous, it looks very suboptimal, but actually that is the genius move, right? Do you think like this setup is more just for more straightforward, like very linear, okay, this is the way, from A to B, there's a clear path to do that task, or it will also do for those more complicated stuff, if that makes sense?
Yeah, so that's a great question. So I don't think we tested that scenario just because I think all the open source data sets we were able to get our hands on, I don't think have that property. And I would say the method probably will trip up on those kind of scenarios because it's, it's the scenario where the original video has something that perhaps doesn't necessarily obey like intuitive physics, right? Like something just magically pops up at the very end.
Well, it could be like a Towers of Hanoi kind of problem would be a good example of this, where you like, it looks like you're undoing progress, but you're not really undoing progress, right?
I see. Yeah, I think we weren't able to test that. And I think the model might be able to do Tower of Hanoi. I wish we just have a video. I mean, we have a live demo on the website. I was thinking maybe we could just like find it.
All right. See if we could.
But I don't think the API key. I'm not sure if the API key works on the website, but I think that raises a pretty interesting question. So I think most of the tasks
definitely do the same Towers of Hanoi that you gave it in the one shot example. Could it do a different order? Is a much trickier question.
Yeah. I'm not super sure because so VLMs is not magic. It does trip up on like a lot of challenging spatial temporal reasoning tasks. So I think in robotics, for most tasks, it seems like sort of straightforward in the sense that, if you ask the human the same problem of like, you can think of this as a puzzle task, right? I present you a bunch of shuffle frames. Can you shuffle them back? There's usually good visual cues for doing it. So I think for those tasks, I think the best models today can do it reasonably okay, like we have demonstrated in a lot of these videos, a lot of these demos. But for really challenging ones, honestly, I'm not super sure.
Like this is a really interesting discussion point, because I also feel like I'd be curious as to whether like the new Gemini 2 robotics models do better or something, right? Because like, for example, a lot of robotics data has these frames that are maybe not super semantically rich. Like they're not the kinds of things that would appear in a language pre-training data set, because like no one's going to describe the Towers of Hanoi setup where like the number 2 smallest ring is on top of the number 4 smallest ring and so on. So maybe the visual features don't capture it super well. Or what do you think? Or does that even make sense?
Yeah, I think that makes sense. Yeah, I'm not super sure since I'm not too familiar with how the newest models are trained, especially I think these days, I think after the paper's release or after we worked on it, there has been emergence of these reasoning models, right? And people are interested in solving visual reasoning problems. And I think the problem I was solving in this paper could be like a visual reasoning task, right? Like, could you look at a sequence of frames and shuffle them back? So actually, there is a literature, maybe like 7-8 years ago, when people were thinking about self-supervised learning in computer vision, they were using like error of time, or the ability to look at 3 frames and tell which one came first and second as a way to supervise vision models to learn better visual features. So I suspect some idea like that could be reapplied to vision language models, especially the reasoning models as they're trying to reason about physical world, right? But, I'm just speculating here, not super sure.
Yeah. Oh, the reason that I bring up the new version of Gemini is because it's supposedly trained more for robotics tasks, right? So like, it feels like there's at least a chance that it has better visual features, like you're saying. Like, although who knows? I guess maybe someone will.
Some of my Google collaborators gonna present this paper at iClear, so Michael could ask them in person if you're going to iClear.
Nice.
Yeah,
iClear's in Singapore. You got to go.
Although honestly, actually, I'm not going to be around in April, but it's a real pity. Yeah, Juf and guys are going to be in town. Yeah, so maybe Jason, maybe we can talk a little bit more about like all the downstream applications of something like what you guys presented. I think those are the really fascinating stuff that I find. Maybe you can start off with, let's say, the in context, like learning stuff. Exactly. The chart that.
No, absolutely. So with this method, right? Like, recall that we are just passing in a sequence of frames, a lot of frames into the VLM. So it turns out at the time, a little bit background, right? Like when I started this project, Google released some of the state-of-the-art long context model, right? Google has the longest context vision language model, or just any foundation model in general. Take up to
2 million tokens or something.
2 million tokens, right?
Yeah.
So if you think about how many tokens a frame take, let's say like, I don't know, we're doing like a vision transformer to packify these images, and each image could be like, I don't know, like 256 tokens, for example. So you could we're passing way more than 30 frames. So what we did in the paper is, in addition to the videos that you care about, that you want to predict task progress, you can actually just pass in more example videos where you present them in the formulation of the task, where you have this video that's shuffled up in different orders, but you also present with the correct, task progress estimation. So those are also just in the context of the vision language model. You provide the examples first, and then now you present the new video that's also shuffled up in random order. And then you ask the model again to predict the progress for these. And it turns out, just by doing that, we actually see performance boost, right? Like you see here. So if we do 0-shot value estimation, progress estimations, then we get, the value order correlation that's, somewhat positive, but not super strong. So one thing I want to say is that on this experiment we tested on in the paper, we call this Aloha 250. So it's basically a very diverse set of tasks we collected on the Aloha setup at DeepMind. And this is much more long horizon and much more difficult than the data sets were tasked in the OpenX embodiment data set. So on average, the model struggles much greater than in the OXC data set. We call that in the OXC, the model 0-shot was close to like very, very positive correlation. But on this data set, 0-shot, you only get very weakly positive. So that's why I was exploring how can we make this model better without having to train this model specifically for this task. So we demonstrated how we can do this multimodal in-context learning, where you can pass in examples in vision and the language modality at the same time, and then get better performance. So here's what you see with one shot, just providing one video example from the same task. You can actually substantially improve the model's capability. And then beyond one example, right? Recall these models have really, really long context. So we can pass in 2 examples, 3 examples, and all the way to 5 examples. So you see that the value order correlation steadily increased from 0 shot all the way to 5 shots, right? Going from very weakly positive to very positive. And if you are in the 0.6, 0.7 regime in terms of linear correlation, then you're actually like very much aligned with the ground truth original order. And this is very exciting for me and for the team, right? Because now we have a method where if you just provide some examples, right? Let's say you do teleoperation twice or 5 times, then that's enough to provide an accurate enough progress estimator that you can use to bootstrap the model's learning on its own, perhaps, right? So this was very exciting, and because you don't have to train models at all to get this capability. And what I think is even more interesting on this note is that recall that we're just passing examples, right? It turns out you could pass an example where, right here, you can pass in examples of the task where it's not the robot that's doing the task. You can actually pass in a human that's doing the same task as well. So now this becomes very much more flexible, where you could have had no demonstration for the robot doing a task and just providing like some human videos of doing a task. And then you just provide that video to the context that will show that also works. Well, of course, it doesn't work as well as having the robot as the example just because of the cross-embodiment gap. But the boost in performance was non-zero, right? And this gave you very cheap way of improving your progress estimator by just having like humans try the task in a bunch of ways. So this really paves the way for making this method really accessible to a variety of settings, because humans just can provide demonstration. And one more thing. So in the appendix, we also have an experiment where instead of
cross-task,
right, instead of the videos coming from the same task, we can actually just show videos of other tasks. Like since we had 250 Aloha tasks, we had this experiment where we just randomly sampled videos from another task as conditioning for a query task. And that also showed positive performance improvement. And that's
what
also very exciting.
What's the value of that? No, yeah, I guess you're about to explain.
Yeah. So the value of that is like, let's say on your setup, you have 10 tasks already, and now you want to learn the 11th task. You want to be able to provide good progress estimation labels for the 11th task. You could just provide examples from the 10 tasks you already collected to boost the performance. And this is really important, has important application in the open world setting. We just want the robot to learn on their own without, having to provide a lot of demonstrations for the robot, right? So you could have just used the repertoire of the skills that the robots have already acquired. There's some video queries, some videos from there, and then do conditioning. And it's really, yeah.
What do you think it's actually doing there? What's the valuable part? Is it like pulling out is it just like you're kind of teaching it, these are what the robot looks like, this is what the robot looks like when it's doing things and that kind of stuff? Okay.
Yeah, absolutely. I think it teaches the model, okay, here's some examples, here's what the robot look like. And if you're like some other tasks the robot's able to solve. So I think implicitly, it kind of tells the model like some notion of, I don't know, like maybe like kinematics of the robot, how the robots can move,
this is
right?
how you solve the tasks with this robot.
Right.
Makes sense. Okay.
Exactly. So that's also helping the model. And I think this is really interesting because I think it really shows how flexible in-context learning could be for VLMs, and especially for robots. Because in robotics, we have this problem that we don't have enough data. This also applies to any task. And here we have flexible ways of boosting the model's capability for one particular robotics application, right? Value estimation, by doing this kind of flexible conditioning. And this got me wonder, what is equivalent of doing this for, like, let's say other tasks in robotics that we care about, such as, captioning or like action prediction, etc. Maybe we can also do this kind of flexible in-context learning to boost the performance. So I think the room and opportunity for future work is fairly plenty in this domain. And I don't think it's fully solved yet. If you look at the Gemini robotics paper, Google recently released Gemini Robotics. You see some examples in context learning, but I think there's just so much more to explore, even with the frontier models.
Yeah. I mean, I also am pretty impressed by the zero-shot performance baseline that you have here. The fact that it's really not that much. I mean, it is obviously 25% lower, but it's like actually fairly high compared to the X embodiment one. I think that's interesting.
Yeah. I think the zero shot performance was really, I think, a surprise to every one of us who's worked on this project at the time, right? Because I think at the time, Gemini 1.4 just came out, and people are exploring all kinds of applications, and I tried this just because in my prior works, I did a lot of work on like doing value predictions. I wanted to see whether or not VLM can zero shot this, one shot this, and just by tweaking the model here and there, like doing the shuffling thing, we were able to unlock this capability, and that was really exciting.
So this is with the shuffling, where you shuffle you just shuffle the images, but you don't provide the context demonstration, and it still gets average of 36% accuracy, I guess, right?
Yeah.
Value correlation.
All the results I'm showing here is shuffle. So in the appendix, we have some results for what happens when you don't shuffle. We can go into that. It's interesting, but when you don't shuffle, the model kind of just gives you degenerate.
Always increases a linear. It always predicts like a linear correlation.
Yeah. Why don't we look at that? I think we had right here, right? So if you do shuffling, shuffle is true, then once you see the task progress, right? Over time, it's not uniformly increasing, right? Depends on the model, the trajectory's actual quality. Sometimes you will go up and down, but if you do not shuffle, then the model would just kind of collapse and give you uniformly increasing output. So, and this plot is that basically we have a bunch of raw outputs from the model and we just overlay them on the same graph, right? Just give you a qualitative trend for what the model's value task progress prediction actually looks like. So you see without shuffling, a lot of times it's always just linearly increasing to 100 or just always predicting 0 without paying much attention to the actual video. Just to show that shuffling is actually very important to get the attention to the.
So this is an artifact of Gemini training though, right? So if you think do you think that in 5 years this will still be the case? I guess.
Yeah. So actually, I think we run this for both Gemini and the GPT-4o. I think both models surprisingly have very similar qualitative behaviors here. As well as quantitative.
Modern LLM training. I assume if you're doing robot data and if you actually were asking it to do this task in language during the training process, maybe it wouldn't happen. I guess it's
absolutely.
Obviously it wouldn't, I guess. So
I think if you actually ask the model to do this task during training, where you provide a bunch of successful video and also failure video, so there is contrast, then I think the model could do this without shuffling. But I think by
putting this paper out there, maybe you're pushing these future versions of the model to already get to solving this better.
Yeah. I would not be surprised at all if people at Frontier Labs just figured, okay, we're just going to put this in the training so it doesn't have this artifact anymore. But I think the shuffling thing is still useful and it's all right? Just because of the shuffleability of good versus bad trajectory. That itself is still useful regardless of whether or not shuffling is needed to get good estimation, right? So I think we can still use shuffling as a way to differentiate trajectories nevertheless. But I think in the future, without shuffling, the model should do better. But again, shuffling is a fairly simple operation. It's np.random.shuffle. So it's not super big overhead. Yeah, would be interesting to see whether or not O1 or Gemini 2.0 could just get away without doing that.
Yeah. I guess just if you can talk about this particular section where you effectively use the ability from this work to essentially give a score to a data set and then take out the bad data and then do behavioral cloning on the better data set. I think that is the wild thing, to me, the biggest wild thing in this paper. You should talk about this one.
Let's talk about it. Yeah, so I think this was, in my prior works on learning value functions, learning task progress estimation, I already had considered applications such as reinforcement learning or doing offline imitation learning on a small data sets. You can filter out bad actions. But what's really, really interesting is when you have a general enough value functions that you don't really need to train on specific data sets for, you can actually use this as a way to tell whether or not a data set on its own, the whole data set is good or bad. And that was really surprising. So how does this work? What does this mean? So recall that like on a trajectory level, we can use VVL's VOC metric to tell good trajectory versus bad trajectory. So you can imagine just running this model method on your whole data set, or like a big subset of your data set, and then compute the average value autocorrelation on all the trajectories you occurred in that data set, and get an average VOC for the data set. And once you have that, you can actually just rank all the different data sets that you have to get a ranking of your data sets. And the hypothesis we had was better data sets for imitation learning should have much higher VOC compared to worse data sets for imitation learning. Why? Because good data set for imitation learning typically would have like good demonstrations, right? Good demonstrations have high VOC, so your data set should have high average. So we run this on the entirety of the OFC data set, whatever OFC data sets that didn't have some processing issue that prevented it to be run. And let me show this, right? So we have this whole table of all the data sets in VOC, in OpenX embodiment. And if you look at the average VOC score for these data sets, they actually make a lot of sense. For the data sets that's actually expert level quality, like the ones that's like curated by human data collection, where the humans are instructed to do good data collection, like the RT1 data set and the Dolby data set, which I think, Chris, you're an author on this paper, if I recall correctly, and also like the Bridge data set, which is where like the lab had a lot of students, a lot of people collect really good demonstrations. They had really high quality. But for the data sets that were autonomous acceleration from the robots, such as QTOP or RoboNet, which is essentially a data set where the robot arm randomly moves around in the scene and touching different objects, then the VOC number is really, really low. And so you can use this as a way to tell the relative quality of different data sets. And then you might ask, why does that matter? Well, so because today, to train the largest robotic foundation models, like vision language models, it's very common to train on a mix of cross-embodiment data sets. You would train on a lot of the data sets at the same time. But prior to this paper and some other papers that came out recently, the researchers that were training these models had to manually tune the relative weight of different data sets, because from a human's perspective, it's really hard for me to a priori tell which data set is better quality, right? So humans, the researcher had to manually tune the different weighting of these data sets. And so you have to do from trial and error to figure out some data sets are actually bad for learning. For instance, there's this really large data set collected by many academic labs called Droid, which I was an author of as well, so I contribute some of the data. In this paper called OpenVL, they found training on Droid actually got the model to like diverge or like not fit the training set very well. And that's because the Droid data set actually has a lot of like trajectories where the camera placement was too arbitrary. So the camera doesn't even contain a lot of the robotic manipulation that's in action. So imagine if you have a video of a robot doing a thing, but the camera actually doesn't capture the robot. Then it's just a bunch of static frames. Shuffle those static frames, you cannot get the original order back, just because all the frames are equally likely to be the first frame, second frame, and so on. So by using
the actual bad examples in Droid.
Exactly. So we have this experiment where, so using this method, we found, okay, Droid surprisingly has really, really low correlation. So we dig into the data set. That's where we found the artifact where a lot of the videos, the cameras doesn't even capture the robot doing the task. So in the appendix, I don't think it's in this version of the paper. In the appendix, we do this experiment where we have a data set from the Droid for co-training, right? So we have a target task we care about, but we wanted to use this diverse data set from Droid to co-train the model so the model can be more robust to, different placements of the object. So we tried this thing where you randomly sample from Droid and compare to using our method to filter the Droid data set to get like a clean, high-quality subset of Droid. And we show that using the high-quality subset of Droid that we were able to clean compared to random sampling, fixing the amount of data, we actually do much, much better. Just to show, if you co-train on low-quality data, it can actually hurt your policy performance. Whereas if you're able to do high-quality data curation, they actually can do much better. So that's something we showed. And I think this is a novel application of past progress estimation that's really, really relevant in today's robot learning literature, where people want to train as much data as possible. And sometimes it's hard to tell which data sets is good, which data set is bad.
I have one other much dumber question now. So RoboNet here is minus 8.85. Minus 1 is complete opposite, right? So like, what happens if you just invert the trajectories in that data set? Like, why is this? Why basically that number doesn't, that correlation being actually the inverse doesn't make sense to me, right? I would think it would be closer to 0, like Droid is, right?
Yeah.
Could you explain that a bit?
Yeah, for sure. So one thing here is that we only took a subset of these data. So, it could be that the real number, if you actually run this method on the whole data set, it could be something else. But I'm actually not super sure why it's like very, very negatively correlated. I think it just happened to be that way. I actually do not have a great explanation for why this particular number stands out. But what I would say is if you just look at some of the really negative ones, is typically when the data sets has a lot of like play data, which is a randomly exploration, or some of these data sets are actually like somewhat corrupted on the OXC format. So like it's just like a bunch of black images. But what I would say is just like when it's really negative, I actually don't think we can
that's one that's
read too much
actually
into
minus
it.
1. Like that means it correctly predicted the complete opposite every single time, right? Like, so that there's something going on there.
Yeah. So this, I admittedly haven't looked into closely very much. So this experiment, we just run it on everything, just get the raw numbers. And I actually don't even know what this data set actually is in OXC. So I think it's worth further investigation. For this one, I'm not super. I think there were some data set that like very, very like static, and I'm not super sure on the super
but if
negative
it's
ones.
static, you should get close to 0, right? Because it can't tell.
Yeah. Right.
Like that looks like someone actually just like loaded the data set in the wrong order, right? I no, sorry, we don't need to go into this. This is very interesting. But okay, cool.
I'm not super sure. So in OXC, I think for people like OpenVLA and those people that actually try to train on it, I think they did have to do a lot of the post processing to make sure all the data is like in good format. So perhaps some of these videos are not uploaded correctly. So I recall some of these data sets actually had corrupted RGB images that contributed to why, even though it's expert demonstration, but the correlation is like kind of non-interpretable. Yeah.
Yeah. Well, I guess the way GVL is set up, like, you can literally do it at the individual video clips level, right? I mean, you're just aggregating result at a data set, but presumably in any given data set, there'll be good data and there'll be so-called bad data. And this seems to me like it's even in the so-called, maybe some of the data set is not so great overall, but there could still be some really gems in there. And it strikes me that having GVL, we just have this tool now to automatically kind of just give me all the good stuff and don't waste any of the good stuff, even though it may be, maybe some data set like I say have a worse setup, but there could still be gems in there so I thought that's just incredible that you can actually do this automatically.
I do want to say though, like in the paper, like I think we're out of time. We were actually trying to use this whole table to retrain like I think RT2 or RTX. Right, because RTX originally had this thing called the magic soup weight, right? So basically, I think one of the original author on the paper sat there and just tuned the weights by themselves. So we were trying to use the method in tune, but we never got around to doing it. But I think it was certainly possible to try. It would be very interesting to try.
How well are those magic weights tuned? How well are those correlated to your VOC scores? That would be also
So if you actually go to RTX or OpenVLA and look at the ones that they actually selected to put in there, so for them, it's not just about VOC, right? It's also about the data quantity. Like these Tokyo data sets are actually very small in size. So even if they have high VOC, for like pre-training, for VLAs, it actually didn't matter that much. But if you look at the data sets that they did include under a large in quantity, you'll notice like the RT1 data set there. I think the Berkeley Auto Lab data set was in there. NYU door opening was typically in those data sets, like the functional manipulation, bridge, right? These are some of the high scoring data sets. They also happen to be the one that's in those pre-training as well. So if you take down the OpenBLA list and put it there, you'll see like a pretty good correlation between the ones that's like put in there and the ones that falling high here.
Yeah,
Do you have
and I remember
downstream
there
results?
was. Chris, you go
Do you
first.
have
Yeah.
any like downstream results from the imitation tuning on RTX, or was that like they ran out of time basically?
No, that's the run out of time experiment.
Okay.
Yeah. Unfortunately, not able to run, but yeah, it would be great to run. Yeah.
Yeah, but if you can, so I think in your figure 8, if I'm not wrong, like I find it quite interesting that so here you basically are saying that roughly if I interpret it correctly, let's say you create the data and anything, let's say beyond 0, like so long it's positive VOC, you kind of include that, and that already gives you the bump, right, in actual success rate. And these are very significant bumps.
Yeah, that's right. So what's happening here is like if you do -1, you have a mixed quality data set, right? You want to use GBL to filter out good versus bad trajectory. If you do -1 filtering, that means you're not filtering anything, right? Because recall the VOC metrics from -1 to 1. That means you just train on the whole data set. So this would be the baseline. This is doing behavioral cloning on your whole data set. But then you can use different threshold to filter out portions of the data set. So we show for all the like numbers we tried, you actually do better than just including a whole data set, because this is somewhat contrived setting where we know some of the data is like low quality, mixed quality, right? But what's interesting here is that there is a sweet spot, right? In terms of like,
Maybe too little data, even.
Right, exactly. If you filter too aggressively, then at some point you just don't have enough data left, right? Even though your data is really, really high quality, there's just not enough of them to do generalization. But then at the opposite spectrum, if you use all your data set, then there's too many bad trajectories that's like polluting your data set. So the sweet spot in our simulated experiments is always like somewhere in the middle. And I think that's good news in practice, because in practice, if you do this in the real world, it's really hard to sweep through parameters in the real world, right? Just because real world evaluation is pretty expensive and noisy. But what this plot tells you is that it's relatively robust to hyperparameter tuning. You can just like set a number and perhaps it would give you some performance boost. So I think that's like good in terms of like trying to use this in the real world.
I'm curious if you had any experiments or thought about any, or even just have any thoughts on how this would work. But like, what if you held the number of experiments constant as you moved through that correlation threshold? Like if I pick 1,000 randomly sampled when my threshold is 0.5, does it do worse than if I pick 1,000 randomly sampled from threshold of 1 or whatever, right? Like, so downsample. So like, if you control for size, does this plot? Yeah, I would expect this plot to just change to a exponential curve up, right? That's what you would hope, unless there is some issue with the value function, right? So do you have any insights in that? What do you think would happen, or did you do something like this?
Yeah, so let me try to understand what you said. So basically, once you filter, maybe you have 1,500 trajectories left, and you just randomly sample 1,000 of them across different values. Is that what?
So let me rephrase. So what you were just saying is that you think that 0.5 is better because it has more data there, right? Like it has but that means that you're conflating two things, right? One of them is how good the VOC score is, right? And the other one is how much data you have. So you could pick a threshold and then sample down to like some fixed floor of number of samples so that you can control for those to actually, and I wonder how this plot would change. What you would hope is that if you did that, it would be just an exponential curve up, right? But
yeah, it will be more drastic. Yeah.
Right. Well, it should never go back down, because hopefully, unless there's some like degeneracy or something in the VOC where it's not actually working properly, right? Does that make sense?
I see.
Or is that?
Yeah.
Okay.
Yeah, that totally makes sense. I think the reason why it goes down here is because there's just not enough trajectory stuff. But in this scenario where even after you do very aggressive filtering, you still have a lot of trajectory stuff. Yeah, I totally see like you can do better, even as you just increase make the filtering more aggressive.
Yeah, it makes sense. So like, okay. Yeah. So you think it probably would just continue to go straight up in that case? Like it would Like maybe you would.
Well, I do want to say at a certain point it has to come down, right? Just because
Right.
if you're really extreme, you set the filter to be 0.999 or something. You only have like, I don't know, like 5 trajectories left. Then you're basically doing behavior code.
Okay, let's throw that out. Let's say I have a hypothetical world where I can somehow keep collecting examples until every single one of them is perfectly correlated, right?
Absolutely.
Like, so then in that case, like maybe it is in simulation. Now, or would that imply something about the language model? Like the other side is that now all of the trajectories literally do look the same because there literally aren't other trajectories that exist where it would get the correct score, right? That is the question.
I see.
Right. And
Yeah.
that comes down to you're relying on pre-trained weights. So how good are they, I guess, right? Does that make sense?
No, I think that would be super interesting to show. Like, I'm thinking of an experiment. I mean, if you have a simulator, you can just sample trajectories, right? So for every trajectories you sample right in RL, you can just use this method to give them a score. So you can just keep sampling until you have like this many trajectories, about 0.9 or 0.8. And then just do BC where the data set size is picked. So I think that would be very interesting because it's possible, one, like, since these VLMs, LMs, and channel finite data is pre-trained, maybe there's only that many trajectories, from a fixed part of your state space that could ever give you above the 0.9 threshold. So it wouldn't actually be exponential, but it could also be the case that, like, doesn't matter where your initial state is, there is some trajectory that can give you about 0.9 threshold. So by doing this way of sampling, you get actually the optimal trajectory across many different parts of your state space. And you imagine if you train on that, then the model would be really, really good because they're training on expert trajectories from all part of the state space, right? So I think that would be like pretty interesting experiment to show. Yeah, but so not in this paper yet.
Right.
Yeah. Okay, cool. I guess, do you have any more things you want to share about the paper? Otherwise, I guess.
I was going to say, there's a tons of additional experiments. I think in the appendix where we did a lot of ablation, also do this for like real world model learning. But I think for the real world model learning part, it's pretty much similar to how traditionally value functions are used. So I think we touched upon all the new like tools in this particular work. So happy to chat with anyone offline as well. Yeah.
Cool. Yeah, maybe just a quick...
How do you think it would work for reinforcement learning? Are we there yet?
Yeah, I mean, that's a good question. So I actually wanted to try reinforcement learning at the time, but then again, as you know, reinforcement learning in the real world is like pretty complex, hard to set up. And so I just never got around getting the infrastructure to set up even. But I think we can use this to do like, couple rounds of like, self-imitation learning, if you will, right? So you can have a BC policy, with imitation learning, you deploy the policy, I don't know, like 100 times. So that gives you 100 additional trajectories. You can use this method to filter good trajectories versus bad, and then train again on all the demonstrations plus the good trajectories and iterate that. So maybe that could show like a couple rounds of like some improvements, but I wouldn't expect that to be like major leap in terms of the model capability, just because you're basically just distilling something that's slightly out of the distribution that the models learned, right? I think for real world RL to take off, you really do need like good exploration mechanism, which is really, really hard to get in robotics. But I do expect that there is prior work that has shown like some round of self-imitation learning for robotics could give you some boost. And I think it's possible to do that with GBL as well. Yeah, I think you can take these processes like one round of like, self-imitation learning, just because the simulation trajectories we have, where we have both successful and failure, are actually just the model royals after one, BC train on expert demo. Yeah.
Right. Yeah. This is a really awesome paper, Jason. I really like it a lot, especially with the downstream applications.
Thank you.
I guess, maybe a couple of usual like round-up questions. If you have like 1 or 2 more months left to finish up this paper, like what would you say are the things that you would have loved to squeeze into this paper?
Yeah, I would have definitely wanted to squeeze in the self-imitation learning stuff, because I was setting this up at the end of my internship. So I did this paper for an internship. At Google, once you leave, you can't really use their infrastructure anymore. I think that's the same for a lot of companies. So I just didn't have the time to wrap everything up I wanted to, but I actually was able to continue some of the work at Stanford, actually, with Professor Dorsa-Sadik's lab and students. So so that's where the droid experiment came from, because her lab had the droid set up. But
Got it.
so I would have wanted to continue keep couple rounds of self-imitation learning going. So that's one. The second thing would just be the RG2X thing that I wanted to try. So I think at the time, the infrastructure internally was changing a lot because there was a merger between DeepMind and Google Brain, I think. So I think a lot of the infrastructure was hard to get to work from the old stack. So so unfortunately wasn't able to run, but would have been very exciting. Yeah.
Someday. Hopefully. Yeah. Very cool.
Someday, yeah. Yeah. I'm sure someone's trying to get this to work very well, in their paper or, in their practical setup. So I would be super excited to see some version of this in like real systems. That would be very exciting. Yeah.
Yeah, I guess maybe as a final question, are there any like recent papers you came across that you're completely mind blown? If you can share, so we can also go and read those.
Yeah. Let me say, completely mind blown. I think on the topic of using vision language models, I think I wouldn't single out any particular paper. I would just say like a general area that I'm super bullish on and super excited about, just because I read a lot of papers in that area these days, would be, using, combining reasoning with vision language models to help with robotics. I think that's fairly exciting. So, we have seen Google doing, I think, Gemini robotics reasoning models. And also we have seen ideas like embodied chain of thought, or ideas like, so I think that's a paper from Berkeley and Stanford. And there's tons of ideas that like incorporating spatial reasoning, right? Maybe using points or using whatever, using the fact that VLM can not only, give you language, but it give you building blocks, give you task progress estimation, all that stuff. So using that to enrich robotic learning, I think that's very exciting to me. And I think there's tons of great work in that area. And one thing I would mention is, if you think about robotic data collection, right? Let's say you're doing Aloha to collect data. That's actually a very compressed form of like human knowledge into robotics data. So what do I mean by that is, when we are doing data collection for robots, right? We actually know a lot about the world. And that's why we can teleoperate the robots in the first place, right? Like humans can pretty much teleoperate any robot if you have a data collection device. And that's precisely because we have so much knowledge about the world that's baked into how we understand how to move Aloha device to collect data, for example. But if you look at robotics data, it's basically a time series of joints. Like a video, right? A video and a time series of joints. That's video to actions. That's really, really like compressing all the knowledge we have into a sequence of like numbers that represent, motor joints, motor torques. So that's a very like compressed form of human knowledge to robotic control. So by expanding the interface between human knowledge to robotics by using VLMs very creatively, I think that would make robots generalize this that much better in the real world. And I think we have seen a lot of papers in this area recently. So that's what I'm super excited about and would love to see more works in that area.
What do you think of the memory piece to solve a lot of like long horizon spatial reasoning? Do you think you just get that out of just longer and longer context window out of these VLMs?
Like when you say memory, you mean like, what do you mean by that?
So for example, the fact, let's say I put something in the drawer, I close it, but I remember that it's inside, right? Things like that we take for granted as humans. But for a longer horizon task, you kind of got to remember, it's like, you play, a poker game, where you put the card, where you flip it, things like that. Do you think we can just get it out of a context window from VLMs?
Yeah, I think that's possible, right? I think another thing you can do is some sort of like retrieval. So in language, people are super excited about retrieval augmented generation, right? So you can imagine like, we know VLMs are good for robotics or useful for robotics. And in the open world setting, your robot has acquired a lot of experience here and there. So maybe there's also a way for us to do retrieval augmented generation for robotics. And I think VLMs as a whole is a pretty general mechanism, right? Just because it's so flexible in terms of inputs and outputs. So I think you could phrase a lot of like tasks in robotics, like, like having memory, right? Or having a history of your robot's execution, feed that into the context of the VLM, and the model can give you something pretty sensible to try. Yeah. I think that's definitely possible. And I think, maybe you can interpret my result in the paper where we do cross-task in-context learning as a form of that. It's like the robot knew, oh, I have done 5 tasks before. How can I use the fact that I was able to solve those 5 tasks to help me predict progress for the future tasks? So certainly possible. Yeah.
In fact, I imagine you can easily do more than 5 shots, right? Given the context window.
Absolutely. Yeah. I think, you can do 10 shots. I don't know, maybe like 100 shots.
Yeah.
Wasn't able to try because some of the API we were using at the time didn't allow us to like, it's just this one project sending a ton of like queries. I think
got it.
They do some load balancing internally. Yeah.
Sure. Yeah, I mean, 30 frames, like 256. So let's say, 6,000-7,000, tokens. You have 1 million. You can definitely squeeze a lot more.
Absolutely.
Yeah, definitely more than 100, I imagine. So you get 100 shots something in a single query.
Yeah. I think in language model, I think it's also people from DeepMind that's called many shots in context learning or something. They show like the performance doesn't plateau up to like 100 shots or something for like some language tasks. I think showing that for robotics would be super cool because, it turns out like these days, people typically collect like 100, 200 demonstrations for a task. And people find state-of-art architecture is good enough to learn a task from 200. So you can imagine just 200 shot into a VLM and the model just does something like really, really good for you. Possible, right? Yeah.
Fascinating stuff. Okay, cool. Well, this has been a fascinating chat. Thank you so much, Jason, for coming on. Cool.
Yeah.
Yeah, we look forward to any future work from you. Yeah. Thanks.
Thank you for having me. It's a super fun conversation. I hope to see you guys soon, in person or online.
Yeah, for sure.
All right.
Cool.
Take care.
All right. Chris,
All right.
what do you think? Yeah. That was really fun.
Yeah, the fun discussion with Jason. So I think, what he has is a method for using like existing large vision language models like Gemini, OpenAI, and basically it turns out that you can estimate task progress and demonstration quality using those very effectively. And you can use those to better train robot policies. And it's really cool to be able to kind of discuss that and see how well you can automatically pull out useful information about the data for robots. Yeah. What did you think, Michael?
I just think that it's incredible that there is such a tool now to give a quantitative score. I mean, even though you can argue that it's not a perfect score, but at least it's a quantitative score that you can measure like how good is the data set, how good, and then from that, then you can do automatic data curation and then presumably do a much better, imitation learning or behavioral cloning, that kind of thing. And so using, you don't need a leap in algorithm, you just need better data curation. And this gets you,
like getting to automatic data curation using these large vision language models working towards that. Because I think it's still like obviously research, but like getting towards that is massive, right? I think that's very valuable to all of us. I agree. I think
I just wonder how much this can be done to the extreme. You kind of push him a little bit on that specific examples, and I think I know what you're talking about, like get the VOC to 0.99 and then but just do a lot of that to 0.99. It's like the perfect examples.
So this is the thing that I think is super interesting, and I feel like a lot of this is in some ways limited by what these large language models are trained on. This is why. So one of the things that I asked him about a bunch of times is like, but do you think Gemini 2 or the Gemini robotics would do better because it is actually trained on robot data? And I think fundamentally, like the difference, if you set, so what we're talking about, so there was this plot where basically like they said that he has the best performance at 0.5. And that's because most of the data is at 0.5 of this correlation metric between the value, right? And I think that the reason that that's a bit, what I'm curious about is like, if you had an unlimited amount of data that's perfectly correlated, would it actually be better? Because if it wasn't, Like that would mean that basically there's that the features aren't good enough for robotics yet, which my intuition is that they're not a lot of the time actually. But like
Yeah.
like but I think they're getting better all the time. So maybe in a few years it would be good enough. Does that make sense?
Yeah, I mean, it's I guess maybe along the same line of that. One of the question I asked him, which is, like it seems to me this will really work for maybe like a simpler task, let's say, which has a very clear path to success, right? It's a linear path, right? But if it gets to be a slightly more long horizon, in fact, it gets very tricky. It's almost like a 3D puzzle, where maybe the last few steps before the final success is actually looks like a very
Yeah,
lousy step, right? So.
exactly.
I wonder, maybe I mean, he also admit as much, maybe, that's where it may start to break down, but it already still, I would say, from large majority of physical tasks, and in a way, maybe some of these longer horizon tasks, you can also just think of it as just a series of subtasks. And so it is already a big unlock, the fact that you can quantify these things.
Yeah, right. Well, like I guess the thing to ask yourself, right, is whether or not
Yeah.
you think Google Gemini can tell the difference between like this robot configuration and like this robot configuration, like where it's all like just in a couple of tokens, maybe different. And this, I was like moving my hand a small amount, but like right, since presumably people might listen to it without the video, but like if there's very small differences like that, I would wonder, and it's not the data set that the language is trained on, then you end up with something with a value function. Maybe that's super important for something like precision grasping, right? Like where I actually really need to get exactly the right configuration to make it work. But that being said, I don't think that it's a fundamental problem. I think that like the technique that he describes would work just as well on like if like the underlying model improves, right? So it's all and the underlying models are improving all the time. So it's interesting though, and I think actually and there's a virtuous cycle here because the more robot data and video gets released and so on, the more that they train on it, right?
Cool. All right. Awesome. Yeah, it's been a good chat. So until the next one.